Hello viewers, welcome to Simple Science. Today I'm going to be introducing you to refraction of light. So this video covers introduction to refraction, and then the subsequent video will cover the practical section and how to answer possible questions that may be set in an external examination. So today I'll be showing you all of these items here: the definition, the effects of refraction, the definition of terms, and then I'll do all of this on the board. We'll look at the laws of refraction, we'll look at Snell's law, we'll also look at refractive index, we'll look at real and apparent depth, critical angle and total internal reflection, and then the formulas for refractive index. So let's get started. The first item we're considering is the definition of refraction of light. So refraction is the bending of light rays as it crosses the boundary between two media of different densities. So what that means is that let's say you have two media. This is air and this is water. And so when light rays travels from air, as it gets to the water, it will bend. It will bend. So because of the different densities, so air has a different density from water. So if this is light and it is traveling, when it gets to the boundary between air and water, it will bend. And that bending is called refraction. It's the bending of light rays as it crosses the boundary between two media. Now, why is it that it bends? The bending of the ray of light is as a result of the difference in the speed of light in the two media. So when light is traveling through air, it has a different speed from when it is traveling through water. So as a result of the difference in the speed of light in the two media, the bending occurs. Now, how is refraction different from reflection? You may have heard of reflection, and refraction is different from reflection in the sense that if you have reflection occurs in the same medium. So if light is traveling in air and it hits an obstacle, it will change direction. It will change direction. It does not cross, it does not pass through the obstacle. It changes direction and it is still in the same medium, still in air or in water. But refraction has to do with two media, and then the light ray crosses the boundary. So that is it for reflection and refraction. Now, refraction is responsible for some of the phenomena we experience in life, we see in life. For example, the apparent depth of a swimming pool is as a result of refraction. What that means is that if you look at a swimming pool from the surface, you will see that the bottom of the swimming pool will appear to be less deep than it is. It will appear to be shallow, whereas it is not really as shallow as it appears to be. So that phenomenon is as a result of refraction. Then also the bending of a rod when placed in a bowl of water. So let's say you have this bowl of water, and then this is a rod. A rod is placed like this. If you look at that rod in the water, it will appear to be somehow bent in the water. You can try it out. In the water, it will appear to be bent instead of it to go straight. This is as a result of refraction. Refraction is responsible for this phenomenon and others. So now the next item is, there are some terms you need to take note of in consideration of refraction, and I will explain those terms. Using refraction through rectangular glass block and refraction through triangular glass prism. So if you have a rectangular glass block like this is glass, and this is air. So let's say light is traveling from air through glass and then it is traveling. So this is a ray of light traveling. At this point, at the boundary between air and glass, it will bend, and then at the boundary between glass and air, it will bend again. So at this point, this ray of light is called the incident ray. Let's say this is, let me label it A, B, C, and D, and then okay. So let's have a normal here. This is a normal. A normal is a line that is at 90 degrees to the surface or the boundary. So let's have another normal here so that we can explain it properly. So we have another normal. This normal is at 90 degrees to the surface, and yet it is at 90 degrees to the surface. So this is our incident ray. Let's call this is our N normal. Let's call this part O. Let's call this part O. Call this point P. Call this point Q, and call this point our R. So this is our normal, and then we have that this line OP is our incident ray, and then this ray in the medium, the ray that is bent is a refracted ray, and then this one that comes out is the emergent ray. And so we have that OP is equal to incident ray, and we have PQ is equal to refracted ray, and Q arrow is the emergent ray. Now the angle between the incident ray and the normal is the incidence angle I, and then the angle between the refracted ray and the normal is the refracted angle R, and the angle between the emergent ray and the normal is the emergent angle of emergence, or emergent angle. Then also for this we also have before we leave this, you will notice that the angle of incidence in air is greater than the angle of refraction in glass. It is because air is less dense than glass. Glass is denser than air. So when light bends, the bending will be towards the normal, and then therefore the angle will be small. So if light is traveling from glass to air, let's say light is traveling, this is the boundary and this is the normal, this is glass, and this is air. If light is traveling from glass to air, this is the angle of incidence. When it gets to the boundary, the bending will be away from the normal. So here the angle will be small and the angle will be big because glass is denser. So if you're considering the angles, the medium with a greater density, we have the smaller angle, whether light is traveling from it to a less dense medium or from a less dense medium to the dense or the denser medium. Then we also come to the triangular glass prism. For the triangular glass prism, you have an equilateral triangle having all sides to be equal, and then let's call this part A, B, and C. You know, for an equilateral triangle, all the sides are equal and all the angles are equal as well. So if all the angles are equal, so this angle is 60 degrees, and then let's say light is traveling in this direction, and then it bends, and at this point it comes out again. So let's put our normal here. This is our normal. Our normal is always at 90 degrees to the boundary surface, the boundary between the two media. Then this is our incident ray. it travels. At this point, it bends. This is our refracted ray, and this is our emergent ray. So this is A, B, C. This is N. So let's call this one Q. Let's call this point arrow. Let's call this point S, and let's call this end T. So Q arrow is the incident ray, arrow S is the refracted ray, and ST is the emergent ray. Let's also put our normal here. Our normal will also come here. The normal is at 90 degrees to the boundary surface. This is the boundary between glass and air. So yes, so now for this, the angle between the incident ray and the normal is the incident angle I, and then the angle between the refracted ray and the normal is arrow, and then also the angle between the emergent ray and the normal, this is our normal, is the emergent angle. So another term that we need to take note of is it's called angle of deviation. So this is the incident ray. If we extend this incident ray, we extend it, and then we extend this emergent ray, we extend it. At this point, we consider this angle D. This angle is D. It's called the angle of deviation. So the angle of deviation is the angle between the incident ray and the emergent ray. And the angle of deviation, we get a minimum value when the angle of incidence is equal to the angle of emergence. So D minimum, the minimum deviation will occur where I is equal to E, where the angle of incidence is equal to the angle of emergence. Then also A is equal to the refracting angle of the prism. The refractive angle of the prism. Now back to this first illustration. For a rectangular glass block, when light is traveling from air through the rectangular glass block, the incident ray and the emergent ray, they are parallel. They are parallel to each other. And so it means that the incident angle is equal to the emergent angle. But in the case of a triangular glass prism, it's not so. And that's why we have to take note of the angle of deviation. Sometimes, if you draw a graph of the deviation against the incident ray, the graph of the angle of deviation against the angle of incidence, we give a curve like this. And then the minimum point of the curve will occur at the point where the deviation is minimum. And then at that point, at the minimum point, the value of I, you have I is equal to E. The angle of incidence will be equal to the angle of emergence. So that's it for this one now. So we've been able to define the incident ray and the incident angle. We have also defined the refracted ray and the refracted angle. We have also defined the emergent ray and the emergent angle. We have equally defined the angle of deviation, and then that's it. Now we go to the laws of refraction. The laws of refraction. So there are two laws of refraction. The first law states that the incident ray, the refracted ray, and the normal, this is the normal, and the normal at the point of incidence, they all lie on the same plane. The incident ray, the refracted ray, and the normal at the point of incidence, they all lie on the same plane. Then the second law states that, let me quickly erase these things. Okay, so the second law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant, for any given pair of media. It states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given pair of media. What that means is that whenever light travels from one medium to another, get the angle of incidence, get the angle of refraction. The sine of the angle of incidence all over the sine of the angle of refraction will give you a constant value. So that's it, and that is also known as Snell's law. It's also known as Snell's law. Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given pair of media. And that takes us to refractive index. Refractive index has a symbol like this. Refractive index is the ratio of the sine of the angle of incidence to the sine of the angle of refraction. There are several formulas for refractive index, and I'm going to show them to you so you know how to calculate the refractive index in different situations and circumstances. But in this case, we have refractive index from air to glass. When light travels from air to glass, the refractive index is equal to the sine of the angle of incidence all over the sine of the angle of refraction. So in this case, light is traveling from air to glass, and then you will notice that the angle of incidence is in air and the angle of refraction is in glass. So when light travels from air through glass, the angle of the refractive index has been found to be equal to 1.5. 1.5. So when light travels from air through glass, the refractive index has been found to be sine I over sine R, which is equal to 1.5. Now, before I go further, I'll draw your attention to the principle of the reversibility of light. Now, the principle of reversibility of light states that the path of travel of light is reversible. What that means is that if light, let's say this is a boundary, light travels like this in this direction, that principle states that if light is traveling in the reverse direction, it will take the exact path it took. So if light is traveling in the opposite direction, now let's say this is air and this is water. So at the boundary, it bends. The principle of reversibility of light has it that if light is traveling back now from water to air and it takes this direction, when it gets to this point, it will take this direction. It will not change. That's what the principle of reversibility of light means, that the direction of travel of light is reversible. And so when light travels from the refractive index now from glass to air will be equal to sine I over sine R, and this will be equal to 1 over 1.5. Remember that if it is now traveling from glass to air, the angle of incidence will be in glass and the angle of refraction will be in air. So sine I will be in glass and then sine R will be in air, and it will be equal to 1 over 1.5. Also from this rectangular, from refraction through rectangular glass prism, we have that refractive index from air to glass is equal to sine half A plus D all over sine half A. Sine half A plus D all over sine half A, where A is equal to the refracting angle of the prism. This is our A, the refractive angle of the prism, and then D is equal to the angle of deviation or angle of minimum deviation. So this is the refractive index. Also, refractive index, when light travels from air to glass, is also equal to the speed of light, or the velocity of light in air, all over the velocity of light in glass. Remember that in the introductory part of this class, I mentioned that the bending occurs due to the difference in the speed of light in the two media. And then we can also use that to express as an expression for the refractive index. So the refractive index, when light travels from air to glass, is the velocity of light in air all over the velocity of light in glass. If you have two medium, say maybe air and water, the refractive index can be expressed as the speed of light in air all over the speed of light in water. That's if light is traveling from air to water. Velocity in the first medium all over the velocity of light in the second medium will give the refractive index. Now, we come to the next item. We have real and apparent depth. Real and apparent depth. And so, for real and apparent depth, remember the first illustration I made, that if you look at a swimming pool, the base of the bottom of the swimming pool appear to be shallower than it actually is. So in the same way, if you have this bowl and then maybe you put something here, a stone here, and you put a stone here, and let's say this is our eye now. We are to look at this stone from this point. This is the surface of the water. This is the surface of the water. You will notice that this stone will appear to be somewhere above the real depth. It will appear to be somewhere above the real depth, and the reason is not far-fetched. It's because of refraction. So the eyes, we see it to be here, whereas in reality it is deeper than it appears to be. So this is the real depth. This is the real depth, and then this depth is the apparent depth. So we have real depth. Sorry, not this one. This depth is the apparent depth. So we have real depth and apparent depth. In this case, the refractive index will be equal to real depth over apparent depth, over the apparent depth. And then we go to critical angle. Now, let's assume that we have a semicircular glass block. These are semicircular glass block, and then this is our normal. This is the midpoint between, let's say, A and B, and this is our normal. This is glass, semicircular glass block, and this is air. So you know that if light travels from glass, at the boundary it will bend. And remember that it will bend away from the normal, because the angle in the denser medium will be smaller than the angle in the less dense medium. Remember that when light travels from air to glass, it will bend close to the normal. So the angle of refraction is smaller than the angle of incidence, because it is from air to glass. So the same way, if light is traveling from glass to air, the angle of incidence will be smaller than the angle of refraction, based on the principle of reversibility of light. So here light is traveling from glass and it's traveling to air, and at the boundary it will bend away from the normal. This is the normal. Now the angle, this is the angle of incidence, this is the angle of refraction. If the angle of incidence increases, the angle of refraction will also increase, because as the angle of incidence increases, the angle of refraction will increase, shifting away from the normal. So it can get to a point, to get to a point, this is the normal. It will get to a point where the angle of refraction will be 90 degrees. This is the incident ray, this is the refracted ray. So when it gets to a point where the angle of refraction in the less dense medium, we are using glass and air. When it gets to a point where the angle of refraction in the less dense medium is 90 degrees, then the angle of incidence in the denser medium is known as the critical angle. So critical angle is the angle of incidence in the denser medium when the angle of refraction in the less dense medium is 90 degrees. And before this time, when light travels from glass to air, this is the refracted ray. We have a weak reflected ray. Weak reflected ray. This ray is weak, is not strong, is weak. And then we have the refracted ray. Now, if the angle of incidence is increased beyond the critical angle, let's say it increases up to this point, we increase it further, the refracted ray will also increase beyond 90 degrees. And then this becomes our incident ray, and then this becomes the refracted ray. Now, we will no more call this refracted ray again, because it is not in air. You know, refraction requires two media, but now because this refracted ray increased into glass, it will become reflection. So this phenomenon is known as total internal reflection, and total internal reflection is the reflection of light ray in the dense medium when the angle of incidence is greater than the critical angle. So that is total internal reflection. I'll take it again. Total internal reflection is the reflection of light rays in the dense medium when the angle of incidence in the dense medium is greater than the critical angle. Now, there are two conditions necessary for total internal reflection to occur. From this diagram, you would see that light is traveling from glass to air, and glass is denser than air. So the first condition that is necessary for total internal reflection to occur is that light must be traveling from a dense medium to a less dense medium, like from glass to air or from water to air. You know, water is denser than air. So the first condition is that light must be traveling from a dense medium to a less dense medium. That is the first condition. And then the second condition is that the angle of incidence in the dense medium must be greater than the critical angle. So these are the two conditions that are necessary for total internal reflection to occur given any two media. And then that brings us to the formulas for refractive index. Now, in this case, the refractive index I is equal to 1 over sine C. 1 over sine C, where C is the critical angle. So we can summarize the formulas for refractive index to be as follows. We have known that refractive index is equal to sine I over sine R. We have known that refractive index is equal to velocity of light in the first medium all over velocity of light in the second medium. We have also seen that it is equal to sine half a plus d all over sine half a, and then we have seen that it is equal to real depth all over apparent depth and we have equally seen that it is equal to 1 over sine c, where c is the critical angle. For this case, experimentally, it has been proven that when light travels from air to glass, the refractive index is equal to 1.5, considering air and glass. The refractive index is 1.5, and then the critical angle C, when light travels from glass to air, the critical angle is equal to 42 degrees. So these are the basics. In the next video, I'm going to probe into the practicality or the practical session of what we have considered, and then we're also going to apply these formulas to see how they work, and we're also going to carry out some other illustrations. So see you in the next class.